So we have a summation problem here. This is the question. These are the two formulas we're going to use. And just to make you happy, I'm going to solve this problem at least twice. I have another video titled Summation Notation in which I promise to come back to this problem. So this is the big moment. All right. One way to solve it is we're going to get rid of the summation notation and just write it out as a long sum. But instead of one long line, we're going to sort of arrange it in a rectangular array. We start with the value k equals 5. So that's 5 squared minus 2 times 5 plus 1. Then we roll up to 6. And I'm going to start a new row. So it's 6 squared minus 2 times 6 plus 1. And so on. We are kind of getting the idea. All the way till the last value of k, which should be 200. Okay. And now we're going to perform the summation column by column. I see 3 columns. The first column is 5 squared plus 6 squared plus 7 squared and so on. Plus 200 squared. The second column is minus 2 times, I'm factoring out this negative 2. 5 plus 6 plus 7 all the way till 200 plus 1, but how many times? This number goes up by 1, so that's good for counting, but it starts with a 5. If we wanted to start with a 1, we want to call this the first row, second row. See, the connection is just subtract 4. So this should be the 196th row, because 200 minus 4 is 196. So 196 times we're adding 1. All right. So now for this first piece, what we're going to do is we're going to add 1 squared plus 2 squared plus 3 squared plus 4 squared. Why? Because we cannot start with 5. If we want to use this formula, we always have to go back to 1 and start there. So that's what we're doing. And now we can compute this sum. And when we're done, we're going to subtract that thing that we added. So basically we have this. We can apply the formula. That's why we added that stuff. We're substituting into the right hand side of this formula with n equals 200. So that's 200. N plus 1 is 201. And 2n plus 1 is 401 divided by 6. That takes care of this sum. And from that, we're subtracting. This is just small enough to do it. 16 plus 9 is 25, 30. So that's the first column. And then the second column, we're going to apply the same trick. So we're going to compute not 5 plus 6 plus, but 1 plus 2 plus 3 plus all the way till 200. Because the formula that we can use always starts from 1. And then when we're done, we subtract that extra 1 plus 2 plus 3 plus 4. And then let's not forget the third column, which we already figured out. Okay, so the formula for the sum without the squares is n times n plus 1 over 2. N is 200, so it's 200 times 201 over 2 minus, this is just 10. 1 plus 2 plus 3 plus 4 is just 10. All right, we're getting there. So we're getting 2,646,686. Okay. The second solution that I want to show you is really no different than the previous one. It's about notation. Some people are not really comfortable with the summation notation. I wasn't for a long time. I still often like to just write out long sums so that I have a better understanding, but some people are very comfortable with that. They can do the following. They can say, well, just like we did the columns, they can say, okay, we have k going from 5 to 200, k squared. Then the second column is negative 2 times 5 plus 6 plus 7 and so on. So that would be, we can factor out the negative 2 and then the summation. This is just compact summation notation, but the same idea is here. So we could say, but we're going to stop. We're not going to repeat the computation. This is the summation from k equals 1 to 200 of k squared minus summation k equals 1 to 4 of k squared. Right? This is how we add and subtract the beginning that we need for the formula. And so on, minus 2 times summation k equals 1 to 200 of k minus 1 to 4. And then from here, we're going to do the same things. We're going to use these formulas. So this is just different with respect to notation. It's a little bit more difficult to understand. You have to filter through the notation. On the other hand, it's less writing, right? It's a more compact. So there is a trade-off, and don't be surprised if you're going to first like one and then the other one. Okay. But I promise you a third way. This is going to be a good way to check our solution. Okay. So this has to do with noticing that this is a complete square. This is actually one of the simplest complete squares. This is just k minus 1 squared, right? K minus 1 squared is k squared minus 2k plus 1. So what is this? If we were to write out, what would be the first piece? The first piece would be 4 squared, right? Because the first value of k is 5, but we're subtracting 1. So we can introduce a new variable, say m is k minus 1. Why? Because then we have this nice formula here. But then when k is 5, m is 4. And when k is 200, m is 199. But look how much easier the whole situation became. This is just 4 squared plus 5 squared plus 199 squared. Which means we're going to add the beginning and then subtract it. And now it's in the form where we can compute it. We're using this formula where n is 199. So n is 199, n plus 1 is 200, and 2n plus 1 should be 399. Divided by 6, minus, this is just small enough to just do it, 5 plus 9 is 14. I'm really hoping we're going to get the same number. With the previous method, we did get the same number. If you're willing to slow down and reflect at the beginning, you might have to compute much less at the end. Thank you for watching.